Hello. Today we are going to be learning about rotational motion. So rotational motion is actually pretty similar to translational motion, which you already know a lot about. However, there are some key changes that we need to note. So in the translational world, we know that the velocity is a change in position over the change in time. Similarly, in the rotational world, we have omega, which is angular velocity, and that's equal to the change in the angle over the change in time. And it's important to note that the change in the angle is measured in radians. We also know in the translational world that acceleration is change in velocity over change in time. In the rotational world, we use alpha, which is the angular acceleration, and that is a change in omega, the angular velocity, over the change in time. Now to the more complex parts. Force is equal to mass times acceleration in the translational world. However, we have torque in the rotational world to model that. Torque is sort of analogous to force. And we know that torque is equal to I, which is the moment of inertia, which is analogous to mass in the translational world, times the angular acceleration. Similarly, for kinetic energy, we have 1/2 mv squared goes to 1/2 times I, the moment of inertia, times omega squared. And we have momentum is equal to mass times velocity, which goes to, you guessed it, moment of inertia times omega. And we use L to represent angular momentum for some unknown reason, but don't forget that.
So what are some key takeaways? Well, the first is that there's some important new terminology like torque, angular frequency, moment of inertia, and you should have a good grasp on what they all represent and all of their translational equivalents. The second is that the same ideas apply, which means you have the same equations, you have the same problem-solving techniques, you should be using the same sort of intuition if you're not sure how to solve a problem at first. And I think the third most important takeaway would be angles, angles, and angles, which is sort of how you get everything in rotational motion to rotate, and it's going to be in names of terms, and it's going to be something that you write on your AP exam when you just have no idea what the answer is to the stupid torque question, and you've already spent 80 minutes on mechanics and you just want to go home.
So perhaps one of the most confusing parts about torque is moment of inertia. So this is analogous to mass, which is basically how much an object can resist acceleration. And so we can think of moment of inertia as how much an object can resist angular acceleration. So obviously if it has a higher moment of inertia, then it will be harder to rotate it. One of the ways to calculate moment of inertia is with the parallel axis theorem. And you'd use this if you have an axis of rotation that you don't know the moment of inertia about. But if you have a different axis of rotation that you do know the moment of inertia about. So for example, in this problem we have an irregularly shaped object of mass m, and we know the moment of inertia at the center of mass, which is I sub COM. And we want to figure out what the moment of inertia is around this blue axis of rotation. So the way we do that is we take the moment of inertia around the center of mass, and we add to that the mass of the object times the length between the two axes of rotation squared.
So, big question on students' minds today is how to calculate torque. So, if you have an axis of rotation and a force at some angle, people will start telling you a lot of things that are very confusing and will hurt your feelings and confuse you. So basically just ignore all that. So the way to think about a force is that it's acting along a straight line in its direction. This is called the line of action. And the line of action is a certain distance from the axis of rotation. So the all you need to know about calculating torque is that it's just the force, its magnitude, times the distance from this line of action to the axis of rotation.
Here we have a simple and popular torque question. So we're given mass 1 connected by a string to mass 2, and that string is around a pulley. So previously we've done problems like these with Newton's laws. However, in this case, we're going to be incorporating torque. So we have a close-up of what it is like on the pulley. And it's important to note that in this scenario, we are assuming that the string does not slip on the pulley. And this is very important because this allows us to write the condition that allows us to solve this problem. So we start by writing our Newton's second law equations. So we have the net force on M2, which is M2A, is equal to M2G, which is the force of gravity pulling it down, minus T2, which is a force of tension pulling M2 up. And similarly, we also write that M1A is equal to T1, because that is the only force acting on M1, because we are assuming no friction on this surface here. Now is time for the torque. Looking here, we see that the string is getting pulled down with T2 and pulled up to the left with T1. So the net force is T2 minus T1. And that is going to be the force that we use for calculating our torque. So we have T2 minus T1, both times R, which is the radius of the pulley and the line of action. And we know that this is equal to I times alpha. Now, because the string does not slip on the pulley, we can also write that alpha R is equal to A. And this is a no slipping condition, and it also means that V is equal to omega times R. And now that we have this equation, we have 4 unknowns, A, T2, T1, and alpha, with 4 equations, and we are able to solve this problem.